Picture this. It's dawn in the year 1294, and you're standing in a field outside the walls of a stubborn castle. The morning mist clings to the ground as dozens of men swarm around what looks like a giant wooden skeleton. This isn't just any construction project. This is the assembly of humanity's most devastating siege weapon, the counterweight Trebuchet. And today, you're going to watch every single step as master engineers transform a pile of timber into a machine that can hurl 300-pound stones over castle walls like they're pebbles. You might think medieval warfare was all about knights, charging with lances, and archers firing volleys of arrows. Well, that's only half the story. The real game changer was siege warfare, and nothing changed the game quite like the counterweight Trebuchet. This wasn't just a bigger catapult, it was a precision instrument of medieval engineering that could knock down walls, destroy towers, and convince even the most stubborn defenders that maybe surrendering wasn't such a bad idea after all. Here's what most people don't realize about these massive machines. They weren't just built and forgotten. Every single trebuchet was a custom engineering project, carefully designed for specific targets and battlefield conditions. The crew we're following today has been doing this for over a decade, and they'll tell you that no two trebuchets are exactly alike. Each one gets adjusted, tweaked, and fine-tuned like a medieval race car. Except, instead of winning trophies, they win sieges. Our story begins before sunrise with Master Robert, a campaign engineer who supervised the construction of over 30 trebuchets across 3 different kingdoms. He's already been awake for 2 hours, checking weather conditions and reviewing the specifications for bat. The timber selection process alone would make any modern carpenter jealous. These today's build. The wind direction matters more than you'd think. Aren't just random pieces of wood. Each the wind's trying to turn it into the world's largest baseball just for aiming, but for the entire construction process. You try lifting a 40-foot timber beam when beam has been carefully chosen based on grain direction, moisture content, and structural requirements. The main throwing arm needs to be made from oak that's been seasoned for at least 3 years, too green, and it'll snap under the massive forces involved. Too old, and it becomes brittle. Master Robert runs his hands along each beam like he's reading Braille, checking for hidden knots or weakness that could spell disaster during operation. The mathematics behind trebuchet design would impress any engineering student today. The optimal ratio between the long arm and short arm is roughly 4:1, but that's just the starting point. The counterweight needs to be precisely calculated based on the projectile weight, desired range, and available construction materials. Too light, and you're basically building an expensive slingshot. Too heavy, and the machine tears itself apart on the first shot. Getting this balance right is what separates master engineers from expensive mistakes. But here's where it gets really interesting and dangerous. The counterweight itself typically weighs between 8,000 and 20,000 pounds. That's roughly the weight of 4 modern cars, all concentrated in a wooden box that needs to drop precisely at the right moment. Moving this much weight around a medieval construction site required techniques that would make modern safety inspectors have nightmares. Teams of oxen, elaborate pulley systems, and more rope than you'd find in a ship's rigging, all came together in a carefully choreographed dance of controlled chaos. The joint work alone tells an incredible story of medieval engineering. These massive machines were held together with mortise-and-tenon joints that had to withstand forces that would make modern construction equipment weep. Each joint was cut by hand with tools that hadn't changed much since Roman times. Yet the precision required was absolutely critical. One poorly cut joint could mean the difference between launching a stone 300 yards or having your entire trebuchet explode into splinters during the first shot. Master Robert's crew consists of 12 specialists, each with their own area of expertise. There's William the joiner, who's been cutting perfect mortise and tenon joints for 20 years. His hands are permanently stained with wood dust, and he can spot a grain flaw from across the construction site. Then there's Thomas the rope master, whose job involves more mathematics than most university scholars ever see. The sling alone requires over 200 feet of specially braided rope, and every knot has to be positioned with surgical precision. The iron hardware presents its own unique challenges. Every bolt, pin, and reinforcement plate has to be forged on site by Henrik the blacksmith. His portable forge has been glowing red hot since before dawn, and the rhythmic hammering of metal on metal provides the soundtrack for the entire construction process. Each piece of hardware is custom made for this specific trebuchet. There's no such thing as standard parts in medieval siege warfare. What really sets counterweight trebuchets apart from their earlier torsion-powered cousins is the sheer amount of energy they can store and release. The physics involved are surprisingly complex. As the counterweight falls, it converts potential energy into kinetic energy, which then gets transferred to the projectile through the throwing arm and sling. The efficiency of this energy transfer depends on dozens of factors, from the pivot point design to the exact moment the sling releases its payload. The trigger mechanism deserves special attention because it's probably the most ingenious part of the entire design. Unlike what you see in movies, there's no simple lever that someone pulls to fire the trebuchet. Instead, there's a carefully designed release system that automatically lets go of the projectile at precisely the right moment in the throwing arc. Getting this timing wrong means your stone either goes straight up into the air or plows into the ground 50 feet in front of you. The construction-rained eyes. Timberby site itself looks like organized chaos to untams lie scattered in seemingly random patterns, but Master Robert knows exactly where each piece belongs. Teams of workers move with practiced efficiency, each person knowing their role in the larger construction sequence. The base frame has to be perfectly level. Even a slight tilt can throw off the entire machine's accuracy by dozens of yards. Safety, or what passed for safety in medieval times, required constant vigilance. A falling timber beam could easily kill 3 men, and the forces involved in trebuchet operation could launch pieces of broken wood like missiles. Master Robert's crew has developed their own system of hand signals and verbal warnings that help coordinate the dangerous work of moving massive components into position. The counterweight box construction is perhaps the most critical phase of the entire project. This isn't just a simple wooden container. It's a precision-engineered component that has to drop straight down without binding or twisting. The guides that keep it moving in a straight line have to be perfectly aligned, and the release mechanism has to function flawlessly under enormous stress. One seized guide rail, and your expensive siege engine becomes an expensive pile of broken wood. But the real magic happens when they start fine-tuning the machine for accuracy. Unlike modern artillery, medieval trebuchets couldn't be aimed using sophisticated instruments or mathematical calculations. Instead, crews developed an almost intuitive understanding of how small adjustments affected projectile flight. Moving the pivot point just 2 inches could change the impact point by 50 yards. Adjusting the release angle by a few degrees might mean the difference between hitting a wall or sailing over it entirely. The projectiles themselves required their own specialized knowledge. Stone balls had to be perfectly round and carefully balanced. Any irregularity would send them tumbling unpredictably through the air. Some siege engineers even developed different types of ammunition for different targets. Solid stone balls for walls, hollow containers filled with incendiary materials for wooden structures, and specially shaped projectiles designed to punch through specific types of fortifications. Master Robert's crew is about to demonstrate why experience matters more than theory in medieval siege warfare. They've built the machine, tested every joint, and calibrated every component. But the real test comes when they load their first practice stone and prepare to unleash the carefully stored energy of 8 tons of falling counterweight. What happens next will determine whether months of preparation result in siege success or spectacular failure. The moment of truth arrives faster than anyone expects. Master Robert raises his weathered hand, and the entire construction site falls silent except for the crackling of Henrik's forge in the distance. This isn't just another test shot. This is the culmination of 3 days of back-breaking work and decades of accumulated knowledge. The crew gathers around their wooden giant like proud parents watching their child take first steps, except their child happens to weigh 12 tons and could accidentally demolish a small village if something goes wrong. The loading process alone requires choreography that would impress a royal dance troupe. 6 men work together to maneuver a 150-pound practice stone into the sling pouch, while 2 others make final adjustments to the release pin angle. Every movement is deliberate and measured because rushing at this stage is like trying to pet a sleeping dragon. It might seem fine until everything suddenly goes wrong. Thomas the rope master checks his sling one final time, running his fingers along every inch of braided hemp to ensure there are no weak spots that could snap under the enormous forces about to be unleashed. Here's something that would surprise most people about trebuchet operation. The crew doesn't actually aim the machine in the traditional sense. Instead, they point it in the general direction of their target and rely on careful calculations and experience to determine exactly when to release the counterweight. It's like trying to throw a baseball while blindfolded, except the baseball weighs as much as a horse, and the consequences of missing could level half a castle wall. The counterweight itself sits ominously in its wooden cradle, looking deceptively peaceful for something that's about to fall with the force of a small earthquake. 12,000 pounds of carefully arranged stone blocks, each one positioned to ensure the weight drops straight down without shifting or binding. Master Robert's team learned the hard way that uneven weight distribution could cause the entire counterweight to swing sideways during release, turning their precision siege engine into a wildly unpredictable wrecking ball. The mathematics of the shot are running through Master Robert's head like an ancient computer program. Wind speed and direction, humidity, temperature, the exact weight of their projectile. Every variable affects the final trajectory. Medieval siege engineers didn't have ballistics computers or weather instruments, but they developed an almost supernatural ability to read environmental conditions and adjust their machines accordingly. Master Robert squints at the morning sky, gauging cloud movement and wind patterns with the same precision a modern meteorologist uses satellite data. William the joiner makes one final inspection of the critical joints, paying special attention to the pivot point where the throwing arm connects to the frame. This single connection point will absorb and redirect forces that could easily tear apart a smaller structure. The mortise-and-tenon joint here isn't just carpentry, it's engineering that has to function flawlessly under stresses that would challenge modern steel construction. One small crack or gap could mean catastrophic failure when 8 tons of counterweight suddenly drops and tries to launch their projectile into the next county. The trigger mechanism draws everyone's attention as Master Robert prepares to activate it. This isn't a simple rope or lever system like you might expect. Instead, it's an ingenious arrangement of pins, hooks, and release catches that automatically fire the projectile at precisely the right moment during the throwing arc. The timing has to be perfect. Release too early, and the stone goes almost straight up. Release too late, and it plows into the ground in front of the machine. Getting this timing right required generations of trial and error, with each successful shot building on centuries of accumulated knowledge. But here's where medieval engineering gets truly impressive. The entire machine has to withstand its own power. When 12,000 pounds drops 8 feet and suddenly jerks to a stop, the forces involved try to tear everything apart. The frame has to absorb and distribute these massive loads while keeping the throwing arm moving in exactly the right arc. It's like building a wooden structure that can survive being hit by lightning, repeatedly and on purpose. The crew takes their positions with practiced efficiency. 2 men stand ready to reset the machine after the shot, while others position themselves to observe the projectile's flight and impact. This isn't just curiosity. Accurate range estimation is crucial for adjusting future shots. Medieval siege crews became expert judges of distance and trajectory, able to estimate projectile flight paths with remarkable accuracy despite having no modern measuring instruments. Henrik the blacksmith wipes his hands on his leather apron and joins the group watching their creation prepare for its first real test. Every piece of custom-forged hardware on this machine represents hours of careful work at the forge. The pivot pins alone took 2 days to create, each one perfectly sized and shaped to handle the enormous rotational forces without binding or breaking. One failed component could destroy weeks of work in a split second of spectacular mechanical failure. The sling hangs ready, its carefully calculated length determining the exact release point of the projectile. Thomas spent hours adjusting this length, because even a few inches difference could dramatically affect range and accuracy. The sling acts like an extension of the throwing arm, effectively doubling the machine's leverage and adding tremendous velocity to the projectile. But this advantage comes at the cost of complexity. The sling has to release at precisely the right moment, or all that extra velocity gets wasted launching stones in completely wrong directions. Master Robert positions himself at the release mechanism, his hands steady despite the magnitude of what's about to happen. 40 years of siege warfare have taught him that confidence and precision matter more than strength or speed. The crew holds its collective breath as he makes final adjustments to the trigger setting. This is the moment when months of planning, days of construction, and generations of engineering knowledge either come together perfectly or explode into expensive splinters. The counterweight waits in perfect balance, suspended between potential energy and kinetic destruction. 12,000 pounds of stone blocks arranged in a wooden framework that would make modern engineers marvel at its simplicity and effectiveness. When this weight falls, it will convert stored potential energy into kinetic energy with an efficiency that rivals modern machines. The physics haven't changed since medieval times, only our understanding of why it works so well. What happens in the next few seconds will determine whether this trebuchet joins the ranks of successful siege engines or becomes another expensive lesson in medieval engineering. The stone sits ready in its sling, the counterweight hangs poised to drop, and Master Robert's finger hovers over the release mechanism. 3 days of construction and decades of experience are about to be tested in one explosive moment of medieval physics in action. The morning wind shifts slightly and Master Robert adjusts his stance accordingly. Even the smallest environmental changes can affect a trebuchet's performance, and experienced siege engineers learn to read these subtle signs, like ancient texts. The success of entire military campaigns often hinged on the ability of crews like this one to adapt their machines to changing conditions and deliver accurate fire when it mattered most. The release pin slides out with a metallic click that somehow manages to sound both insignificant and earth-shattering at the same time. For a split second, nothing happens. The counterweight hovers in its guides like it's reconsidering the whole arrangement. Then physics takes over with a vengeance that would make Isaac Newton applaud, assuming he'd been born about 4 centuries earlier and had a thing for medieval destruction. 12,000 pounds of stone blocks plummet earthward with the inevitability of taxes and bad weather. The wooden guides shriek under the strain as the counterweight box accelerates downward, converting potential energy into kinetic energy at a rate that would impress modern physicists. The throwing arm, which had been resting peacefully against its stop, suddenly whips upward like an angry giant's finger pointing accusations at the sky. The sound alone is worth the price of admission to this medieval engineering demonstration. First comes the thunderous crash of the counterweight, hitting its stop at the bottom of its travel, a noise like Thor dropping his hammer in an empty cathedral. Then there's the sharp crack of the throwing arm reaching the end of its arc, followed immediately by the distinctive whoosh of a 150-pound stone ball departing the sling at speeds that would make a modern pitcher weep with envy. But here's where the real magic of trebuchet engineering reveals itself. The sling doesn't just fling the projectile forward, it actually adds a whipping motion that dramatically increases the stone's velocity. As the throwing arm reaches its maximum height, The sling continues its arc for a few more crucial feet, essentially doubling the effective length of the throwing arm. It's like having a medieval physics lesson demonstrated with enough force to knock down castle walls. The projectile arcs through the morning air in what appears to be slow motion, though it's actually travelling at nearly 200 feet per second. Master Robert and his crew watch with the intensity of parents at their child's first school performance, except their child happens to be a flying boulder that could accidentally demolish someone's house if they miscalculated the trajectory. The stone reaches its apex about 150 feet above the ground, hangs there for a moment like it's enjoying the view, then begins its descent toward the target area they've marked out roughly 300 yards away. The impact sends up a cloud of dirt and grass that would make a small explosion jealous. Even from their position near the trebuchet, the crew can feel the ground shake slightly as 150 pounds of limestone announces its arrival to the local landscape. Master Robert nods with satisfaction. Not celebration, mind you, but the quiet approval of a craftsman whose work has performed exactly as intended. The shot landed within 20 yards of their target marker, which in medieval siege warfare terms is basically threading a needle while riding a galloping horse. Henrik the blacksmith is already inspecting the machine for stress fractures or failed components. The forces involved in trebuchet operation are hard enough on the wooden components, but the metal hardware takes a particularly savage beating. Every pin, bolt, and reinforcement plate has to withstand sudden shock loads that would challenge modern steel construction. One failed pivot pin could turn their precision siege engine into the world's most expensive pile of firewood. William the joiner runs his hands along the throwing arm, checking for cracks or splits that might have developed during the shot. The arm itself flexes considerably during operation, not by design, but because wood simply can't be made rigid enough to eliminate all bending under these massive forces. The trick is ensuring that the arm flexes predictably and returns to its original shape after each shot. Too much flex, and accuracy suffers. Too little flex, and the arm snaps like a toothpick. Thomas the rope master is examining his sling with the intensity of a detective at a crime scene. The sling takes more abuse than any other single component, since it has to accelerate the projectile from 0 to nearly 200 feet per second in the span of about 3 feet. The braided hemp fibers show signs of stretching and wear, but nothing that suggests immediate replacement is necessary. A good sling could survive several hundred shots if properly maintained, but recognizing when wear was approaching dangerous levels required experience that couldn't be learned from books. The counterweight box sits peacefully in its bottom position, looking innocent despite having just participated in a demonstration of controlled violence. The wooden guides show fresh scuff marks where the box scraped against them during its 8-foot plunge, but the alignment remains true. Master Robert examines the release mechanism that allows the counterweight to drop, a surprisingly simple arrangement of ropes and pulleys that has to function flawlessly under enormous stress. But one successful shot doesn't make a siege engine. The real test of any trebuchet is consistency, the ability to put projectile after projectile into the same general area with enough accuracy to actually damage fortifications. Medieval siege warfare wasn't about spectacular single shots. It was about methodical destruction, knocking down walls one stone at a time until defenders decided that surrender looked more attractive than becoming part of the rubble. The crew immediately begins preparing for their second shot, a process that reveals just how much work goes into each individual launch. The counterweight has to be raised back to its starting position using an elaborate system of pulleys and winches that would make a ship's rigging master nod with approval. 6 men working together can raise 12,000 pounds about 8 feet in roughly 10 minutes, assuming everything goes smoothly and nobody drops any ropes or forgets to set the proper brake positions. Reloading the projectile is its own specialized art form. The stone has to be perfectly positioned in the sling pouch, with its weight distributed evenly to prevent wobbling during flight. Even small irregularities in projectile shape or weight distribution can send stones tumbling unpredictably through the air, making accurate fire nearly impossible. Some siege engineers became so particular about their ammunition that they would personally inspect every stone before allowing it to be loaded. The fine-tuning process between shots is where medieval engineering becomes almost mystical in its precision. Master Robert makes tiny adjustments to the release pin angle, changes measured in fractions of inches that can alter the impact point by dozens of yards. He adjusts the counterweight position slightly, moving individual stone blocks to change the center of gravity by perhaps 2 inches. These microscopic modifications require an understanding of physics that most university scholars of the time couldn't match. Weather conditions play a much larger role in trebuchet accuracy than most people realize. A 10-mile-per-hour crosswind can push a 150-pound projectile several yards off target during its 6-second flight time. Changes in air density due to temperature and humidity affect how quickly the stone loses velocity. Even the direction of the sun can influence accuracy, since crew members need to clearly see their target area to make proper adjustments. The mathematics involved in trebuchet operation would challenge modern engineers. Yet medieval siege crews solved these problems through experience and intuition rather than formal calculations. They learned to estimate projectile weights by hefting them, judge distances by eye, and predict wind effects by watching grass movement or smoke patterns. Master Robert can estimate the weight of a stone ball to within 5 pounds just by lifting it, a skill that took decades to develop. The loading sequence for the second shot proceeds with mechanical precision. Each crew member knows exactly where to position himself and what tasks to complete in what order. The counterweight rises slowly up its guides, held in place by an arrangement of ropes and catches that would make a ship's rigging master weep with admiration. The throwing arm settles back against its wooden stop with a solid thunk that signals the machine is ready for another demonstration of medieval physics. But this time, Master Robert makes a small adjustment that demonstrates the sophisticated understanding these crews had of their machines. He moves the release pin exactly 1 inch to the left, a change so subtle that most observers wouldn't even notice it. This tiny modification will alter the release timing by perhaps 1/10 of a second, enough to change the impact point by 15 yards. It's the difference between hitting a wall and missing it entirely. The second shot reveals why trebuchet crews were considered specialists rather than common soldiers. The stone lands within 10 yards of their target marker, close enough to the first impact point to prove that their machine is capable of consistent accuracy. In siege warfare terms, this level of precision was the difference between success and expensive failure. A trebuchet that could reliably hit the same section of wall shot after shot could breach almost any fortification given enough time and ammunition. Henrik examines the pivot point, where the throwing arm connects to the frame, looking for signs of wear or loosening that could affect future shots. The forces concentrated at this single point are enormous. Imagine trying to stop a falling tree with a wooden peg, except the tree weighs 12 tons and is trying to launch itself into orbit. The joint shows some fresh wear marks, but appears to be handling the stress without significant damage. The crew's efficiency in resetting and firing their machine would impress any modern artillery unit. From impact to ready to fire again takes roughly 15 minutes with an experienced crew working smoothly together. This rate of fire might seem slow by modern standards, but it was devastatingly effective against medieval fortifications that simply weren't designed to withstand this kind of systematic bombardment. Master Robert calls for a third shot, this time with a heavier projectile, a 200-pound stone ball that will test the machine's ability to handle increased payload weights. The physics of trebuchet operation means that heavier projectiles don't necessarily travel shorter distances, but they do require adjustments to release timing and counterweight positioning. The crew makes these modifications with practiced efficiency, each man knowing exactly how changes in projectile weight affect his particular area of responsibility. The heavier projectile changes everything about the machine's behavior, and watching Master Robert's crew adapt demonstrates why these men commanded premium wages in medieval warfare. Thomas the Rope Master immediately recognizes that his sling will experience significantly more stress during release, so he makes a subtle adjustment to the knot positioning that redistributes the load more evenly across the braided hemp fibers. It's the kind of detail that separates experienced siege crews from the ones who end up explaining to their commanders why their expensive war machine just turned itself into kindling. William the Joiner examines the throwing arm joints with renewed intensity, knowing that the additional weight will test every connection point beyond its previous limits. The mortise and tenon joints that looked perfectly adequate for 150-pound stones now face stresses that could reveal hidden flaws in the woodwork. He runs his fingers along each joint line, feeling for the microscopic gaps that might indicate loosening under load. One failed joint at the wrong moment could send a 200-pound stone ball in any direction except the intended one. The counterweight positioning becomes critical with heavier ammunition. Master Robert personally supervises the rearrangement of stone blocks within the counterweight box, moving individual pieces to optimize the center of gravity for maximum energy transfer. It's like tuning a massive wooden piano, except instead of producing music, you're trying to produce consistent ballistic performance. 2 inches in the wrong direction could mean the difference between punching through a castle wall or bouncing harmlessly off its base. Loading the heavier stone requires a different technique entirely. 6 men instead of 4 guide the projectile into position, while 2 others adjust the sling pouch to accommodate the increased size and weight. The stone itself has been carefully selected not just for weight, but for shape. Perfectly round stones fly truer than irregular ones, and at these velocities, even small asymmetries can send projectiles wildly off course. Master Robert inspects the surface personally, looking for chips or flat spots that could affect aerodynamics. The physics of the heavier shot are fascinating to anyone who understands medieval engineering principles. The increased projectile weight doesn't proportionally reduce range because the counterweight system is so efficient at transferring energy. Instead, the trajectory becomes flatter and more direct, which actually improves accuracy at medium ranges. It's counterintuitive until you understand that trebuchets aren't just giant slingshots. They're sophisticated energy conversion machines that happen to be made of wood and rope. Henrik the blacksmith pays special attention to the release mechanism, knowing that the increased forces will test his metalwork beyond anything the previous shots demanded. The trigger system has to function flawlessly under loads that would crush most medieval hardware. Each pin and catch has been forged to tolerances that would impress modern machinists, using techniques passed down through generations of siege warfare specialists. One sticky release could delay the shot just enough to send their projectile into the ground or over their target entirely. The crew takes their positions with heightened awareness that this shot represents a significant escalation in the forces involved. The men responsible for resetting the machine after firing position themselves slightly farther away, knowing that component failure under these loads could launch pieces of broken wood like missiles. Medieval siege warfare taught harsh lessons about standing too close to powerful machines under stress, and experienced crews learn to respect the destructive potential of their own equipment. Master Robert makes his final adjustments to the release pin with the precision of a clockmaker. The heavier projectile requires a slightly different release angle to achieve optimal trajectory, and getting this calculation wrong could waste not just the shot, but potentially damage the machine. He's done these calculations thousands of times over his career, but each shot is unique. Different projectile weight, different weather conditions, different target requirements. The mathematics exist only in his head, accumulated through decades of practical experience. The wind conditions have shifted slightly since their previous shots, requiring another round of minute adjustments that demonstrate the incredible sensitivity of these machines to environmental factors. A breeze that wouldn't move a feather could push a 200-pound stone several yards off target during its flight time. Master Robert watches smoke from Henrik's forge, grass movement in the distance, and even the way morning dew behaves on nearby surfaces to gauge atmospheric conditions with an accuracy that would challenge modern meteorological instruments. The moment arrives with the same dramatic tension as before, but the stakes feel higher with the increased projectile weight. Master Robert's finger hovers over the release mechanism as he makes final mental calculations about wind compensation and trajectory optimization. The crew watches with the intensity of gamblers waiting for dice to stop rolling, except their bet involves several weeks' wages worth of construction materials and the reputation of their engineering skills. The release comes with a mechanical authority that sounds different from the lighter shots, deeper, more resonant, like the machine itself recognizes the increased seriousness of its task. The counterweight drops with the same thunderous impact, but the throwing arm's acceleration seems more dramatic, more purposeful. The forces involved in launching 200 pounds at nearly 180 feet per second create stresses that push medieval engineering to its absolute limits. The projectile's flight path looks different too, lower, more direct, with less of the arcing trajectory that characterized the lighter shots. Physics governs everything about trebuchet performance, and heavier projectiles follow flatter paths that can be more accurate at medium ranges but require different aiming techniques. The stone disappears into the distance like a cannonball, though cannons won't be invented for another century, and medieval crews achieve similar ballistic performance using nothing but wood, rope, and accumulated knowledge. The impact creates a more substantial crater than the previous shots, testament to the increased kinetic energy delivered by the heavier projectile. The crew can actually feel the ground vibration more distinctly this time, and the cloud of dirt and debris reaches higher into the morning air. More importantly for siege warfare purposes, the stone lands within 12 yards of their intended target. Accuracy that would allow systematic destruction of fortification walls through repeated bombardment of the same structural points. But this demonstration reveals something crucial about trebuchet operation that modern people often miss. These weren't just bigger versions of simple catapults. They were precision instruments capable of consistent accuracy that could be fine-tuned for specific tactical requirements. A crew like Master Roberts could adjust their machine to deliver different types of ammunition at various ranges with reliability that made them invaluable assets in medieval warfare. The post-shot inspection becomes even more critical with the increased stresses involved in the heavier projectile launch. Every component shows signs of the elevated forces. Fresh wear marks on the pivot points, slight compression in the wooden joints, microscopic stretching in the ropework. None of these changes indicate immediate failure, but they represent the gradual accumulation of stress that eventually requires component replacement or machine rebuilding. Henrik examines his metalwork with particular attention to the stress points where iron meets wood under maximum load. The custom forged pins and reinforcements have to absorb and distribute forces that would shatter standard medieval hardware. His portable forge continues glowing red-hot nearby, ready to repair or replace any components that show signs of dangerous wear. In siege warfare, having backup hardware often meant the difference between continued bombardment and expensive delays while new parts were manufactured. Thomas the Rope Master inspects his sling with growing concern about wear patterns that become more pronounced with heavier ammunition. The braided hemp fibers show signs of stretching and friction damage that weren't visible after the lighter shots. Sling failure during operation could be catastrophic, not just for accuracy, but potentially dangerous for crew members positioned near the machine. Medieval siege crews learned to replace worn components before they failed, rather than risk spectacular mechanical disasters. William the Joiner continues his systematic examination of every wooden joint and connection, knowing that the accumulated stress from multiple heavy shots could reveal weaknesses that weren't apparent during construction. The throwing arm shows slight compression where it bears against its stop, and some of the frame joints display microscopic gaps that indicate settling under load. These changes are normal and expected, but they require careful monitoring to prevent sudden failures. Master Robert calls for ammunition adjustment, deciding to test the machine's versatility with a different type of projectile entirely. Instead of solid stone balls, they're going to load what medieval siege crews called a scatter shot, a leather bag filled with smaller stones that would spread out after release. This type of ammunition was particularly effective against personnel on castle walls, though it required different trajectory calculations and release timing to achieve optimal spread patterns. The crew's expertise becomes evident as they adapt their procedures for the specialized ammunition. The scatter shot weighs roughly the same as their previous projectile, but behaves completely differently in flight. The leather container has to be positioned precisely in the sling to ensure it opens at the right point in the trajectory, spreading its contents across the target area rather than delivering them as a concentrated impact. This final demonstration reveals the true sophistication of counterweight trebuchet technology. These machines weren't just siege weapons. They were versatile artillery systems capable of delivering various types of ammunition with predictable accuracy. A skilled crew could switch between wall-breaking stone balls, personnel-clearing scatter shots, and even incendiary containers, depending on tactical requirements, all using the same basic machine with minor adjustments to operating parameters. The versatility demonstration shows why trebuchet crews were considered elite specialists rather than common soldiers, and why their services commanded premium compensation in medieval warfare economics. The scattershot loading process reveals engineering challenges that would make modern artillery crews appreciate their standardized ammunition. Unlike solid stone balls that sit predictably in the sling pouch, the leather container requires careful positioning to ensure it opens at exactly the right moment during flight. Too early, and the contents scatter uselessly in front of the target. Too late, and you've essentially launched an expensive leather bag that delivers about as much damage as an angry pillow fight. Thomas the Rope Master makes subtle adjustments to the sling configuration, shortening one side by exactly 3 inches to create an asymmetrical release that will cause the container to tumble during flight. This tumbling motion is crucial. It creates the aerodynamic instability needed to tear open the leather and spread the contents across a wide area. It's like trying to program a medieval computer using nothing but rope geometry and accumulated experience from watching hundreds of previous shots. The mathematics involved in scattershot trajectory planning would challenge any modern ballistics expert. Master Robert has to calculate not just where the container will be when it opens, but how wind resistance and tumbling motion will affect the spread pattern of dozens of individual stones. Each small stone follows its own ballistic path once released from the container, creating a cone of destruction that requires entirely different aiming techniques than solid projectiles. Henrik examines the specialized release pin they're using for this shot, a custom piece that creates a slightly delayed trigger action. The timing difference is measured in fractions of seconds, but it's enough to alter the release point just enough to optimize the scatter pattern. This level of precision metalworking would impress any modern machinist, yet Henrik accomplished it using hand tools and a portable forge that wouldn't look out of place in a Roman military camp. The crew positions themselves differently for the scatter shot, spreading out to observe the impact pattern across a wider area. Unlike solid projectiles that create single impact craters, scatter shots produce dozens of individual impacts spread across an area roughly the size of a castle courtyard. Medieval siege crews learned to read these impact patterns like ancient forensic scientists, using the distribution to calculate wind effects and trajectory optimization for future shots. William the Joiner makes one final inspection of the throwing arm joints, knowing that the asymmetrical forces created by the tumbling projectile will stress the machine in ways that perfectly balanced loads don't. The arm has to withstand not just the normal launching stresses, but also the twisting forces created by a projectile that's deliberately designed to fly erratically. Medieval engineering had to account for these unconventional load patterns using nothing but experience and intuitive understanding of wood behavior under stress. Master Robert's final adjustments to the counterweight position seem almost mystical in their precision. He moves individual stone blocks by distances measured in fingers rather than inches, creating a weight distribution that will optimize energy transfer to a projectile designed to behave unpredictably. The physics involved are complex enough to challenge modern computer simulations, yet he's solving these problems through pattern recognition developed over decades of practical experience. The weather conditions have continued shifting throughout the morning, requiring constant recalculation of environmental factors. The scattershot's multiple small projectiles are even more susceptible to wind effects than solid stones, since each individual piece presents a different surface area to the breeze. Master Robert watches distant smoke patterns and grass movement with the intensity of a meteorologist preparing a forecast that could determine the success of an entire military campaign. The ammunition itself tells an interesting story about medieval logistics and supply chain management. The leather container was hand-sewn, using techniques that ensure it will tear apart predictably under stress, while the stones inside were individually selected for size and weight consistency. Creating effective scattershot ammunition required skills from multiple craftsmen, leather workers, stonemasons, and siege specialists, all contributed to what appears to be a simple bag of rocks. The final scattershot releases with the same thunderous authority, but this time the projectile's behavior tells a completely different story. The leather container tumbles through its arc exactly as planned, tearing open at the perfect moment to spread dozens of stones across the target area like medieval buckshot. Master Robert nods with the quiet satisfaction of a craftsman whose decades of experience have once again transformed raw physics into battlefield precision. From sunrise timber selection to this final demonstration of versatility, we've watched 12 specialists transform a pile of oak beams into a machine that could change the outcome of sieges and reshape the medieval world. These weren't just weapons, they were masterpieces of engineering that proved human ingenuity could harness the fundamental forces of nature using nothing but wood, rope, iron, and accumulated wisdom passed down through generations of siege warfare.